So we were talking about how to find the pressure drop across a duct, okay? And we said that we will do a general analysis that will be valid for any cross-sectional area of the duct. So if it's circular, if it's square, and even we will do a general analysis that can work if we have change in cross-section, okay? So this is why we considered a very an infinitesimal control volume of thickness dz, and we did the analysis of forces acting on it, okay? And we said mainly since we have we neglect gravity forces because the given told us that gravity forces are neglected, so we would still have pressure forces and shear forces. So by representing the forces acting on the on our control volume, we are now ready to apply the conservation of linear momentum equation on this control volume. So if we do so, let us go back to the general relation, general momentum relation. This is the general momentum relation. You have that summation integral. So first you have sum of external forces. In our problem, what are the external forces of interest in the problem we are considering? We have just pressure forces and we have shear forces, okay? Because gravity is neglected from the given and we don't have any other force acting on our system. So these are the two main forces that we will consider. Now, since we have a steady application, it's a steady, fully developed flow, so we don't have a transient term. So whenever we talk about a steady flow, del by del t term will cancel out. So we will only have to deal with this term, which will consider the different momentum entering and leaving our control volume. What is simple here is that the control volume we are considering has a constant cross-sectional area. So when you consider this control volume, you have that the flux in is equal to the momentum flux getting out. Why? Because the inlet section and the outlet section here are of same area. Therefore, we know already that due to continuity equation for a steady flow, m dot in is equal to m dot out. Plus, we have that the cross-sectional area is the same. So A inlet equals A outlet. Whenever we have these two conditions and we are dealing with an incompressible flow, if we write then the expression of m dot, we know that m dot in is rho times area times V inlet, and m dot out is rho. So this is A in, and this is A out. So rho times A out times V out. So since it's an incompressible fluid, rho will cancel out. Since we have the same cross-sectional area, A in and A out will cancel out. So we end up with V inlet equals to V outlet. And it's not only in magnitude, but also in direction, because both are perpendicular to this cross-section, and we have both along same sense. So we deduce that vector velocity V in is equal to vector velocity V out, and therefore no change in momentum through our control volume. Because as we have seen together, this term will end up with, when we have a constant velocity going through the system, or even here, you don't have constant velocity through your cross-section, you have a second degree variation. You have a parabolic profile, but this parabolic profile is not changing from section to section. So you have exactly the same profile, okay? So since I have the same profile as these two cross sections, then I will deduce that when I perform the integration for the inlet and the integration over the outlet, since the profile of velocity is the same for both, then what will happen is that the inlet momentum flux will be equal to the outlet momentum flux, and therefore this term will cancel out. So what is the condition here for this term to cancel out? Is that the momentum entering flux is equal to the momentum leaving flux. And this is valid here because I have the same, I don't have a change in the cross-sectional area, and I don't have a change in the profile of my velocity. Okay, so I will end up then with this term canceling out, and I will just have sum of forces equal to 0. So I can deduce that for any case, if I don't have change in the cross-section, if I have a duct with uniform cross-section, okay, and I'm dealing with a steady application, then fluxes of momentum in equal to flux of momentum out, and therefore this term also will cancel out, and I will end up with sum of forces on this system equal to 0. Okay, so now what I will do is just to apply this relation for my problem. So going back to my problem, I have only the pressure and shear forces acting on my system. Okay, so all I have to do then is to write that this term, okay, this term will cancel out, so integration over the control surface. Why? Because we noted that along z direction, velocity out of the control volume equals that into the control volume. So this will make this right hand side equal to 0. So we end up with that sum of forces acting on our control volume equals to 0. Now, if we do balance of forces, going back to our free body diagram here, this is the free body diagram of our system. From the free body diagram, the forces acting on our control volume are just the pressure forces and the shear forces. Okay, so we have, if we consider this is our positive direction, so we will have plus P times A minus P plus dP times A, and the shear forces are doing an action in the negative direction. They represent frictional forces, so it's minus shear force times the area of the control surface we are considering. And as we mentioned before, to make it a general demonstration for any cross-sectional geometry, so you can have a square duct, you can have a circular duct, you can have a rectangular duct. So to make your analysis valid for any geometry, we will just replace the cross-sectional area by the perimeter P times the thickness dz. So if I have, let's say, a square, just I have to know what is the edge A, and the perimeter will be 4 times A. So this is P if I have a square duct. If I have a circular duct, okay, then what will happen is that my P will be equal to 2 pi r. If I have a rectangular duct, then I will deal with, if this is A and this is B, then my P will be equal to 2A plus 2B. Okay, and of course the velocity profile in a circular duct is different than the velocity profile in a square duct. So then they should give me the profile, the velocity profile, and the function variation for each geometry. So supposing that I know how the velocity is varying within my different geometries, then here in this application, the velocity profile will not affect my balance, because just I need to know that since I'm doing a steady, fully developed application, the velocity profile is not changing with cross section. So this will give me a net momentum change that is zero. So for whatever is my velocity profile, when I apply the balance equation for forces, I will have sum of forces just equal to zero. So I don't care for the geometry. The only condition is that I have a uniform cross section. Because once I have a uniform cross section, if it's a square or a circle or a rectangle, the velocity profile will not vary because I'm dealing with steady, fully developed applications. So the balance of entering and exiting momentum fluxes, linear momentum fluxes, will cancel out. And for all cases, I will end up with sum of forces equals to zero. And since I will have for all these cases sum of forces equal to zero, then this analysis is general and can be applied for any uniform cross-sectional area. And therefore, when I apply it, when I put the balance, I will get plus P times A minus P plus dP times A minus the shear stress times P dz equals to zero. And now when I perform this, okay, I can find an expression for my pressure drop. Why? Because this term, if I develop it, it's minus PA and minus dP times A. So P plus PA minus PA will cancel out. So I will end up with the following terms. I will end up with shear TW, the wall shear stress, times the perimeter of my cross section, times dz is equal to, so is equal to, if I take minus dp times a to the other side, so this is equal to plus dp times a. Okay, and now if I consider, if I take dz to this side and a to the other side, this is what I will get. I will get that the variation of pressure with z, and this was the question, find the equation for the pressure drop. So this represents the pressure drop with z, along z. The pressure drop along z is minus the shear stress times P over A. Okay? So if I do a physical interpretation of this, first it's a negative result, and this is expected. Why? Because as my flow will move along the duct, okay, due to frictional effects from the surface of the tube, what will happen is that friction will decrease the pressure in my flow. This is why dP by dZz is the axial direction. So dP by dz will be negative. And of course, larger is the shear stress. So larger is the friction, if you want, per unit, friction force per unit area. This will lead to larger values of pressure drop. Okay? Because larger friction forces will lead to larger pressure drop. And larger is the perimeter of my duct, also larger will be the pressure drop. It's logical, because larger is the perimeter. This means that larger is the frictional contact surface. So if I increase the frictional contact surface, then the pressure drop will increase. Okay, so this represents for me, this equation will represent for me the pressure drop, and this pressure drop is inversely proportional to the cross-sectional area, because you know that, okay, we know that when we write the expression of the force is P times A, the pressure forces, okay? So when I do the balance between pressure forces and shear forces, so for the same total shear force, larger is the cross-sectional area, lower will be the value of P. This is why pressure gradient is inversely proportional to the cross-sectional area of my dome. Okay. So now if you want, you are able to calculate the pressure drop over any length of interest. So let's say I give you a duct, okay, and I tell you that I want to find what is the pressure drop between 2 points A and B in the fully developed region. So let's say this is L, okay. From this analysis, tau is a constant here. Why it's a constant? Because tau is mu times del V or del U over del R for a circular duct. For a square duct, let's say, you will take the direction, you can take a direction, a y direction, and you put its mu times del U by del Y. Okay, so for any of these cases, since we said that the profile will be the same, so for a circular duct, I'll have the same profile everywhere. So due to this effect, okay, what will happen is that this term will also be constant, whatever is my cross section. And since I have uniform cross sections, the perimeter also is the same everywhere. So this term and the cross sectional area also. So this term will be a constant. So since it's a constant, then whenever I have the slope is a constant, then if I integrate this equation, I can deduce that delta P is equal to minus this constant times delta Z. Okay, so here, for example, if I'm doing the analysis between points A and B, I can say that the pressure drop, so PB minus PA, pressure at B minus pressure at A, should be equal to minus the constant is, I can replace the constant by its value, so it's minus the wall shear stress times the perimeter of the circular duct, which is 2 pi r, over the area. Here for the circular duct it's pi r squared, so times delta Z. Delta Z is here, ZB minus ZA, it's equal to the length L. So this will allow me to determine what is the pressure drop over a certain length. Okay, of course this analysis will be much more complicated if I have a variation in the cross-sectional area. So what I mean by this, let's say if you go through a diffuser, okay, so let us say we have a diffuser, then we have variation in cross-sectional area. You will repeat the same procedure of analysis, okay, but now it will be more complicated because since you have the area that is varying, then the momentum flux that is coming in will be different from the momentum flux that is going out. And you should perform a more complex analysis that will allow you to come up with also a differential equation that can be integrated to find delta. So here just we developed the technique. You can apply it to any general case. So whatever is your flow, you will do the same procedure. You take a control volume. You will do the analysis of forces acting on it. You will do the analysis of entering and exiting momentum fluxes, and you will write your balance. And this will allow you to find how your pressure will vary as your flow is moving within your system. Okay, so this is for continuity and momentum equation. So as you can see, in general, momentum and continuity equations should be coupled to come up with a solution. Because when I want to solve for a momentum equation, I will need m dot. So finding m dot will be required to pass to the momentum equation. So keep in mind that these conservation laws should be used together to end up with the appropriate solution. Okay.